In this video, we'll discuss about watches and notifications. Because Zookeeper is typically accessed as a remote service, accessing a Z node every time a client needs to know its content would be very expensive, as it would induce higher latency and more operations to a Zookeeper installation. So consider this figure. So here in this figure, client C2 reads the list of tasks and returns initially empty. Then client C2 reads Z node again to determine whether there are new tasks or not. And this second call to get children / task return the same value, that is an empty set. Then client C1 creates a new task and client C2 reads again and observes the change. Here task -1. So now in the figure, as we can see that the second call to get children / task returns the same value, that is an empty set, so it is consequently unnecessary. And this is the common problem with polling. To replace the client polling, we have opted for a mechanism based on notifications, where clients register with Zookeeper to receive notification of changes to Z nodes. Registering to receive a notification for a given Z node consists of setting a watch. A watch is one shot operation, which means that it triggers one notification. To receive multiple notifications over time, the client must set a new watch upon receiving each notification. So in the situation illustrated in this figure, the client reads new values from Zookeeper when it receives a notification, indicating the value of /task has changed. So in this figure, what is happening is that first of all, client C2 reads the list of tasks that is initially empty, and then it sets a watch for changes. Now client C1 create a task, that means that a change has occurred, and when there is a change, the client is notified. Then client C2 reads the children of /task and observes the new task. Now when using the notifications, there are few things to be aware of. Because notifications are one-shot operations, it is possible that new changes will occur to a Z node between a client receiving a notification for the Z node and setting a new watch. So suppose the following events happen in this order. First, client C1 sets a watch for changes to the data of /task. Then second, client C2 comes and adds a task to /task. Third, client C1 receives the notification. And fourth, client C1 sets a new watch, but before it does it, a third client C3 comes and adds a new task to /task. So now client C1 eventually has this new watch set, but no notification is triggered by the change made by C3. And to observe this change, C1 has to actually read the state of /task, which it does when setting the watch, because we set watches with operations that read the state of Zookeeper. Consequently, C1 does not miss any changes. One important guarantee of notifications is that they are delivered to a client before any other change is made to the same Z node. If a client sets a watch to a Z node and there are two consecutive updates to the Z node, the client receives the notification after the first update and before it has a chance to observe the second update by, say, reading the Z node data. The key property we satisfy is the one that notifications preserve the order of updates the client observes. Although changes to the state of Zookeeper may end up propagating more slowly to any given client, there is a guarantee that clients observe changes to the Zookeeper state according to a global order. Zookeeper produces different types of notifications depending on how the watch corresponding to the notification was set. A client can set a watch for changes to the data of a Z node, changes to the children of a Z node, or a Z node being created or deleted. So to set a watch, we can use any of the calls in the API that read the state of Zookeeper. These API calls give the option of passing a watcher object or using the default watcher. And so that was all about watches and notifications.